Hey guys. Okay, let me share the screen. Can you please let me know if you can see the slides? Okay, perfect. Just wait for a few seconds here so people can join. How is everybody doing? Usual? Okay. Yeah, don't know. Keep hearing about getting back to normal soon. So I hope this will change everybody's mood, and spring also is coming. So this is very all good signs. Behind on lectures. Yeah, it's always like this. I don't know. Yeah, I think this is one of the kind of, the common characteristics in the university. It's like, you tend to focus on one subject and then you lose, following up with others. But unfortunately, that's a price you have to pay for getting education for a professional degree. But I hope things will get better. So at least um, I'll have to tell you, the people attending the lectures, I guess, just keep this contact between you and the material, even though you don't have the time to follow up and study and solve problems. But it is much, much better than kind of, ignoring the whole thing, entirely. So for the people attending the lecture, I guess you will have no problem really to catch up. Also, the problem analysis session is giving you an opportunity to kind of, have one-on-one discussion with the TA and also your friends. So try to make use of this, kind of available resources to you. Okay, so we'll have to keep going. So today we have, I would say, like the first official kind of, important part of the fluid mechanics after we learn a little bit on different topics. Today we're going to talk about like the fluids, the fluid flow, which is basically, it's like, 95% of the fluid mechanics application in engineering field is relating the parameter that you learn, the analysis that we keep kind of approaching as we discuss in the previous chapters, apply to a fluid motion, right? So we need to see how the fluid is moving from one point to another point. So many of these systems is basically require some analysis in order to find out, for example, what will be the energy needed in order to drive this fluid in the system. Okay, so all engineers will be dealing with certain application of these fluid flow analysis. So the content of this chapter that will be that we're going to cover. So those are the only pieces in chapter 6 that we're going to focus on in this few lectures. Basically, first, look at the flow in the ducts, and ducts in general could be piping or could be, non-circular ducts. Flow in straight pipes, flow in straight pipes, and also through components like valves and orifices, bends, and fittings, and why the needs of these fittings in the system. And at the end, if you sorry, just let me enable this. Okay, and the last part will be related to how much energy, how much, in terms of you want to move the fluid inside the system. If this fluid is liquid, we call the device needed for moving this fluid, we call it a pump. So what will be the energy of this pump? You know, what will be the rating of this pump? 2 kilowatts, 5 kilowatts, 100 kilowatts. What is the energy or the power required to drive this pump? Or if we need to move like gases, so we're talking about compressor in this case. Again, we need to find out what will be the required energy to move these fluids or these gases in these systems. Okay. So application for this is massive, like, you know, you'll see it everywhere, right? Starting from the transportation of oil, like between cities or between, like, you know, the supply and the source. And in many process industry, petrochemical industry, or any type of industry that you're thinking of fluid moving inside the system, you will see piping, and you'll see, like, you know, different configuration of this piping and piping components. You know, this could be power generation facility, you know, you name it, like, you know, any production facility will, like, you know, you will have piping that is carrying fluids. And what you need as an engineer, either to design this piping system or to monitor the performance of the pump or the equipment driving the fluid in this piping system, or, like, you know, do some modification inside this piping system, or, like, you know, at least when you have some kind of monitoring devices for the pressure and temperature and other things, you need to know how to deal with the analysis of the fluid flow inside the system. So very wide range of application. And not all the time we are talking about liquid, but we can talk about gases in this case, or ventilation, or like, you know, heating equipment. It's basically driving fluids or driving, you know, air in this facility, starting from your own home to big building to big industrial facility. All these duct that is carrying fluids, we need to understand how can we do the analysis for this fluid inside these ducts. Okay. Application is, as I mentioned, wide range. Wastewater, you know, system, like, you know, drainage system in cities, or the supplying water distribution system in the city or between cities. All these application is kind of, you know, involve like fluid flow in pipes or ducts. Not only limited to mechanical system, and you know, but it could also included in the biological you know, system, when we're talking about our own body and the blood flow in between, you know, organs. In addition to electronic cooling, and you know, this could be like, you know, a fan that is driving this air around the electronic component, or even driving, you know, liquid, you know, nitrogen, just like, you know, for cooling application in these cooling devices. Okay, so very wide ranges of application. Just before we getting into the subjects, I'm gonna, you know, share with you you know, a very classical video for what we call it Reynolds experiments, because the most important piece of you know, if information I want to carry at this lecture here is, it's, you know, in order to analyze the flow inside the system, we have to really characterize this flow. We have to really say, oh, what is actually the physical phenomena in these, the flow moving inside the system? What will be the, you know, the ratio between these, remember, the shear forces and the viscous forces inside the system? What kind of losses that we need to evaluate in this system? Okay, one of the very important experiment that is done in fluid mechanics is called Reynolds experiment. And you might, you know, remember Reynolds here is, it is related to the Reynolds number that we discussed in the previous chapter. Okay, we develop a non-dimensionless quantity, and we call it Reynolds number. And this Reynolds number is, you know, it is becoming very important from one aspect, which is, you know, it is a non-dimensional group of, you know, of parameters inside this fluid, and it is representing physically the ratio between, you know, inertia force and viscous force. How this is important into the calculation or the analysis of the fluid inside the system is, we have to know what is this Reynolds number means. What this Reynolds number indicating? Okay, so you remember our experiment of Reynolds number. We said, yes, that's Adam. That's basically what we are trying to discuss here. I'm happy that you guys at least familiar with these backgrounds. So so in order to define, you know, the flow characteristic, we're gonna run what we call a Reynolds experiment, and this Reynolds experiment is relating rho v. Let's just sorry. So Reynolds number here is rho v d over mu or v d over nu. If you remember, nu is mu over rho, right? So relating density, velocity, and diameter over the viscosity, this is what the Reynolds experiment is. So we allow fluid to move in the pipe with different velocity by opening the valve and just allowing more flow to go. We know the diameter of the pipe, we know the density of the pipe, the viscosity, and we run the experiment several times. So if we have the same fluid, that means rho and u are the same, diameter is the same, but now we are changing the velocity to increase the number over a wide range of of condition, and monitor, you know, what will be the the flow physics inside this pipe. So in order to do this, imagine if we have water and you run fluid inside this pipe, you will not see anything. It's going to be like a clear, because the water itself is a transparent fluid, right? So what we're going to do is, like, we're going to inject, you know, a dye at the center of this pipe. And this dye, what is only doing is, you know, plotting what we call it the streak line. If you remember in chapter 4, we called the streak line is, you know, the trace of this dye, which is the fluid particle is carrying this dye and drawing, you know, the motion of this liquid motion. So let me just stop sharing this and then try to open the video. I hope we can run it. Let me try. Okay, share here. So can you see this? Can you see the new screen now? Yeah, yes, okay. So now,
this glass pipe.
Can you see the video running and hearing the voice? Okay, perfect.
Which is attached to a container, is carrying water. At some point in the pipe, a coloured pigment is introduced into the flow. A man called Osborne Reynolds observed that when the velocity of the flow was low, a simple undisturbed coloured trickle was seen to flow along the pipe. This orderly, stable flow in a fluid is known as laminar flow. However, when the velocity of the flow increases, the coloured trickle becomes increasingly unstable, and with any further increase in the flow velocity, a turbulent and violent flow of the liquid ensues. This is called turbulent flow. If we study the flow of fluids with different viscosities and change the diameter of the pipe, we will see that the transition from laminar to turbulent flow in a pipe always occurs at the same value. This value is known as the Reynolds number and is equal to the fluid velocity along the pipe axis multiplied by the diameter of the pipe divided by the kinematic viscosity of the fluid. This combination of the flow parameters is known as Reynolds number. In the pipe, the transition from laminar to turbulent flow occurs at a Reynolds number of 2,300.
Okay, so let me just go back to the slide here. Okay. So you can imagine, like, this experiment is showing like how the particle of the fluid moving in the case of laminar flow, okay, and in the case of turbulent flow. So for laminar flow, as you know, we've seen in the video, the particle is moving in a very, you know, nice steady lines, right? So all the particle, you can imagine this now as all the particle on inside this pipe, the layers. So one layer, you know, the layer that is, you know, let me just do this. So imagine now I have, this is a piping wall, right? And now I have layer of these fluids, and this layer is far from the center here, R, right? So now let me ask you, for a pipe, what will be the first layer? This is at the wall here. Okay, so the first layer here, imagine this is a circular pipe. So it's gonna have, we have a first cylinder of fluid, cylinder of the particle of the fluid in contact with the pipe wall. What will be the velocity in this case at this pipe wall? 0, right? As you go down, as you go, you know, as another, you know, cylinder just a little bit away from the wall, the velocity basically increases. Okay, keep increasing. If you keep going into, you know, the center of the pipe, where is the maximum velocity that you think of, like, you know, in this pipe here? Where is the maximum velocity located? So at the center, right? So if we imagine now this pipe flow is moving almost like a steady cylinders inside each other, and then at the center is your maximum velocity, the fluid moving here in a kind of, you know, in the form of layer, which mean that viscous forces, the viscous forces between this layer is very dominant, because this fluid is moving as layers, right? And that's why the viscosity is dominant. So if you look at the, you know, the Reynolds number here is inertia over viscous force. Okay, so when you have a viscous force that is very high, Reynolds number is when you have, exactly, right? So that's why laminar flow, you have the viscous effect is more, like, you know, the viscous forces are more dominant than the inertial forces, and that's why you will see the fluid characteristic is defined in this way. And that's why we don't have to run different velocity, different viscosity, different, you know, diameter and so on, but now we have what we call it a non-dimensional number. Every time we calculate the combination of these parameters, we end up with, you know, something that is equivalent to all these cases. For all these experiments, it looks the same just before Reynolds number becoming about like a 2000. Okay, so, you know, 2000, 2300, all these, you know, the number here is not a very rigid number, like, you know, but, you know, something below the 2000, it is basically representing similar behavior of the fluid inside this pipe. So Reynolds number here is representing what we call it, you know, the low Reynolds number here below this is basically representing laminar flow. It's called nu land, right? So nu here is like, you know, you just go back to the kinematic viscosity, yes. Okay, so if you go back to the first chapter, you will see this. So it's kind of, so now once you start increasing Reynolds number by increasing the velocity, you know, the particle is start moving up and down, right? So the particle starts, you know, moving like this and like this, right? So which means that there is more, you know, exchange of momentum between the particle. The particle that has higher velocity in the middle goes up a little bit to mix with the particle that is moving with a lower velocity, and then so on, right? Until you reach to the point where the whole particle in the fluid is actually mixed, right? So I'm talking here about, like, you know, a particle that is moving at the center now moved, you know, all the way up, and then just like move, and then, like, you know, those parts. But at the end, all the fluid is moving in this direction. But some of this particle is moving, you know, mixing with the other particle. Okay. So what do you think about the velocity in this case? You know, the velocity inside this pipe. Is it going to be more homogeneous, more like alike or very close to each other in the turbulent cases, or in the laminar cases? Which one will be more kind of, you know, evenly distributed for the velocity? Laminar? Oh my God. Evenly distributed. If the particle moves up and down and mixing with other particle. So do you think the velocity total will be kind of more kind of combined together, like, you know, the smaller velocity mixed with the higher velocity, creating like a big, you know, a big number of these, or like a, right? So turbulent is mixing more. So mixing mean, you know, the velocity distribution inside the pipe will be a little bit more flat, like it almost same. I'm gonna explain this a little bit more as we get into the slide, but just to keep in mind that Reynolds number is a number, you know, is basically telling you that you have a laminar flow or viscous or turbulent flow, basically describing what we call it the flow regime. Okay, so we call the flow regime in this case. So now flow regime that is laminar, we are expecting the flow to behave in a certain way. If the flow regime is turbulent, we are, you know, expecting the flow to behave in a different way. The transient is a condition that we don't deal with too much as an engineer, okay? Because this condition between turbulent and laminar are a very small little area between the two, which is not all the time as an engineer we should design system that is working on a transient kind of, you know, condition for this, right? So in this case, you will see the transient case is not that much, you know, paid attention and when it comes to engineering application. But of course, when they're talking about engineering sciences and people are interested in a very critical location where the fluid has to be transient, there's no way. So you have to really get much more kind of, you know, complex analysis for that. Okay. Other experiments, you know, like Reynolds experiment is a free surface flow. Like, you know, they have a jet. This is basically, this is a pipe or a hose, right? And the flow just going out, you know, to the atmospheric, right? So free surface here is be atmospheric, right? So outside the atmosphere. If you have a very, like, and you can try this by yourself, like, you know, with a garden hose, if you start opening the valve slightly, you will see the jet is very smooth like this. But when you start increasing the, you know, the flow rate, or you open the valve a little bit more, you will start having these waves, you know, of this, you know, of the jet. Okay, so we call this is again, you know, some indication of the value for Reynolds number that is, you know, indicating laminar or turbulent type of flow. Okay. So this is what I mean by, you know, the velocity distribution. Okay, you remember in chapter 5 we said that, you know, in order to develop relation for this complex phenomena, you know, we might end up with using what we call it the dimensionless analysis. Okay, for a pipe like this, the fluid coming, let's say, from a tank or from, you know, a huge reservoir, and now getting into the pipe. Okay, you will see some variation of this velocity profile. Okay, we call the first part here is the entrance region. So the fluid start, you know, kind of, you know, moving as if it's like a turbulent type of case, and then what we call it here, we call it a boundary line. I don't want to get too much complex in this phenomena here, but this boundary layer here is referring to the area where the shear stress is, like, you know, the variation of the velocity because of the viscous shear stress closer to the wall. Okay, once this shear stress boundary layer becoming almost at the center of the pipe, you will see the velocity distribution inside this pipe. It looks like this. Okay, and this is basically what this is a center line, right? And as you go in this direction here, you are going from the center, and as you go closer to the wall, the velocity becoming zero. Okay, the distance between where the fluid is coming from the tank with all the disturbance, just the fluid try to, you know, get inside this duct here. You know what will happen in the beginning, you know, is going to be some kind of some turbulence happening, and that's why you will see the velocity distribution here is almost flat in this case. So the distance between this point and the point where the fluid almost become what we call it fully developed. It is like if you now measure the velocity at any location downstream here is going to be the same, right? So if you measure the velocity, it will be the same. So this is becoming repeated velocity distribution. Okay, we call it a fully developed flow. This length here, the length at which the fluid become what we call it fully developed, okay, is where the shear stresses, okay, and the pressure drop are equivalent. So the pressure drop mean as you go inside the pipe or as you go along the pipe here, the pressure is dropping, okay, because this is a constant diameter pipe. So, and it's horizontal, so the velocity is not changing, you know, the inertia is not changing because, or the velocity is not changing, and also the potential is not changing. That means the pressure has to decrease in the direction of the flow, right? So once the pressure drop is the pressure drop forces or the pressure variation forces are kind of, you know, equivalent with the shear, viscous shear forces, you will see a linear relation between, you know, this pressure and the X. So at this location here, we call it a fully developed flow. Because it's a very complex phenomena in this region here was non-developing region, or just before the fully developed. That's why we come up with, you know, some relation between these fully developed lengths and the other fluid parameters. Okay, same way as we did for in chapter 5, the dimensionless analysis. We know this length is a function of the diameter, the velocity, the density, and the viscosity, and we can end up with the, you know, the length over d. So how many downstream of this entrance here, you know, the fluid become fully developed, and we end up relating this development length with what we call it, you know, rho Vd over mu, which is our Reynolds number. So this entrance region will be different for laminar flow versus turbulent flow, and those numbers can be determined by experiment, and then we can find out those relations. Okay, the extent of this slide here, what I want you to know is that the fluid is actually can change because it goes through some variation. Like, you know, this tank, huge tank, the fluid almost stagnant inside. Now the fluid come inside the pipe, and the fluid try to reorganize itself, right? So it takes time. So which means that there are something called developing lengths, like a flow that is developing to the point it's becoming almost repeated and the same characteristic later on. So this fully development length, it depends on the flow characteristic, if this is a very fast flow like turbulent flow or laminar flow. And the relation between L over D. And why L over D? Because if you remember in the non-dimensional analysis, we try to relate most of the diameter here, the property, we put it in a non-dimensional form. So the length with respect to the diameter, that's a very nice, you know, ratio that we can say. So for example, we can say for laminar flow, it is about 60 diameter. Okay, so it takes about 60 diameter or 50 diameter downstream of this, you know, entrance region for the flow to become fully developed. For turbulent flow, because it's like, you know, turbulent is almost flat profile, it's L over D is about 10 to 12 or 15 diameter downstream. Okay, so those are relation here just to show you what is the connection between what we learned in our chapter 5 and what we are talking here about the flow in the pipe and ducts. Okay, and this is something for your information. So piping system, you know, most of this piping that is carrying fluid from one point to another point is not going to be only a straight pipe, and it's not going to be only a straight pipe with the same diameter. It might have different diameters connected together with elbow, with reducer or expansions, right? So as you go inside this piping, this is kind of a, looks like to me is a firefighting, you know, system. So you can see here, this is like, you know, the sprinkler heads, right? So you will see here the piping, they contain like manual valve, like, you know, some, you know, connections here, you know, elbow, you know, connection for these nozzles and so on. So piping system will contain many components, right? Part of it, it's straight pipe, and part of it is what we call it, you know, fittings, right? So pipe fittings, and this pipe fitting has a wide range of pipe fittings. So in this chapter, we're gonna cover what is, the losses inside the straight pipe, and then we talk about like, the losses in these fittings. And then we consider at the end of the chapter looking at the total losses in the system if you go from point 1 to point 2. So let's start with the first part of this lecture today, which is talking about the friction losses. Okay, so once we start talking about like a straight pipe, okay, which means that this pipe is going, same diameter, so the diameter of this pipe is the same everywhere. Okay, now we call this is a straight pipe. Okay, and the straight pipe, the only losses that we have in this pipe here is what we call it the viscous forces in between the fluid and the pipe, and we call this is the friction losses. Of course, like the fluid and itself, there are some viscous forces, right? That's why when you look at the velocity profile here, so this is the velocity here and the velocity here are different. And the velocity here are different, right? What is changing the velocity between this point here and this point here? What is the main reason for the fluid velocity to decrease as you go closer to the wall? Never say that again, Lan. Not elevation. The fluid is moving, right? The center of the pipe here, right? It's like, yeah, I know it's you're talking about elevation from here, but the elevation is along the pipe, along this, along this line, is not across the cross section. So elevation here has nothing to do with the velocity here, right? This is a velocity distribution at the same section. No, don't be sorry. I'm just saying that. Just try to remember, this discussion. So I know what you mean, like by elevation here, but elevation here never like, think about it, the elevation across the pipe cross section. Okay. It is always, when we're talking about elevation and potential heads, we are talking about a point in a pipe, right? And another point downstream on this pipe. So never across the pipe cross section. Okay. So viscous, yes. So basically shear stresses and viscous forces, right? So if you go from one point here, right, and another point here, right, it's basically because of the viscous forces between the fluid and itself, right? Those layer, if you remember the layer that we were talking about, or the, the fluid moving here and the fluid moving there, there's some viscous forces between those layers. I hope you can see my, my hand here, right? So, and as you keep going closer to the wall, now you will have more friction forces between after the different layers, okay, the different layers inside the pipe. Okay, as you go closer to the wall, the velocity decreases, yes, and because of friction, you remember we said friction between the fluid and itself, but now we have, okay, exactly, that's one, right? So it is going to be a viscous forces between the fluid and the wall, right? And the wall, whatever the wall is, like, even though it's a glass wall, still have some kind of roughness. The pipe, the material of the pipe will have some kind of, roughness in these pipes. So we will see, like, a viscous forces between the pipe and the fluid. Okay. So when we are talking about straight pipe, what will be the velocity or the flow rate at point 1 and at point 2 here? Let me just go here. Maybe just one step here. No. This point 1 here, this point 2 here. If you remember our datum, this is Z1, this is Z2, okay? We are all the time considering the pipe as a line, right? This is the center line of the pipe, okay? So in this case, potential change is Z1 and Z2, okay? Now, can you tell me this is constant? Diameter pipe, oops. Okay, constant diameter pipe. Oh my God. What is the Q at 1 and the Q at 2? Q, of course, is basically the cross section, right? Flow rate at 1 and flow rate at 2. It means at the section 1 and at the section 2. What is the flow rate at 1 versus the flow rate at 2? Same, right? Why? Because the diameter is the same, the area is the same. That means Q1 is equal Q2, okay? Or the V1 is equal V2 because area is the same for constant diameter pipe. So if I apply Bernoulli equation between 1 and 2, right? Pressure, velocity square over 2g plus potential, pressure, velocity square over 2g plus potential heads, right? This is at 1 and this is at 2. And, you know, just ignore this alpha here because v square over 2g is a kinetic energy. But alpha here is considering if the velocity, you know, profile or the velocity distribution is not uniform, right? So there are some factor here. But again, those are the 3 terms of the Bernoulli equation, right? And those are the 3 terms at point 2. The difference between 1 and 2 is what we call it, like, you know, the friction losses, okay? And these friction losses here can be represented by what we call it the shear stress, okay? We don't need to really look into how did we determine these value. If you remember in chapter 4, we talk about something called the differential equation for the momentum and energy. We did not cover it in this course because it required much more time to develop this. So we didn't talk about Navier-Stokes equation, for example, and all this, but at the end, you know, we just try to focus on what is the most important pieces in our course. So the friction force here is represented by the shear forces, okay, the diameter of the pipe, the length of the pipe, and so on. So we can find out the friction losses here by this equation, okay. So in this equation here is FL V square over 2GD. Okay, so then the losses in the friction here is developed by some scientists in the past, and then they developed this using the differential form of of the fluid velocity inside the pipe. They apply the momentum equation and the energy equation, and they end up with relating these H loss fraction as function of these parameters. Okay. If you remember, we said not all the time we will be able to correlate fluid parameters. That's why sometimes we use the dimensionless analysis. So you will see here, for example, this F here, the friction coefficient, is determined as a function of Reynolds number, the relative roughness, and the duct shape. Okay, so in general, our losses of the friction is FL V square over 2GD, where F here is a function of Reynolds number, epsilon over D, and epsilon here is your roughness of the pipe. So this is a pipe roughness, okay? And the duct shape here, it's whether the duct is circular or a different type of shape, okay? So friction losses here is determined experimentally, because if you remember, we said we're going to run an experiment, but in order to minimize the number of experiments we have to run, that's why we put everything in a non-dimensional form. And that's why you will see the friction factor here is a function of a non-dimensional group. Okay. So fully developed pipe flow, F here is 64 over Reynolds number. Okay, the people who are wanna, find out how did we determine this fraction factor as a function of real number like this. You really have to go and look at the the procedure and the analysis in the textbook if you would like to do this. This is a very common Darcy-Weisbach factor, and it is determined for laminar flow using the Navier-Stokes equation that we just refer to it in chapter 4. Okay, so at the end, the related the fraction factor as a function of a Reynolds number. So if you know the Reynolds number in the pipe, you can find out the fraction factor in your case, and then you can determine what will be the losses over a certain length of the pipe using this equation here. So we have H loss fraction is F L over D V square over 2G. If you want to remember it this way. Okay, so you have the length, you have the diameter, you get the friction factor, you know the velocity, you can find out H loss fraction. Okay. There is other correlation for this, because I mentioned that this is only for laminar flow. So you can expect for turbulent flow, because the velocity itself it's a very complex to determine this velocity. Is going to be some value that is average and then fluctuating value. So the turbulent flow is much more complex to determine parameter of for this type of flow. That's why we develop correlations for that, and those correlations are made of lots of experiments. Okay, so so we have the Colebrook equation, right? And it is basically developed by Frank Colebrook, right? And he basically what he did is like he got a lots of piping materials, piping diameters, and then he determined what we call it the epsilon over D. This is what we call it relative roughness. So epsilon here is is dependent on the machining of the pipe, the material of the pipe. D here is the diameter of the pipe. So this epsilon over D is a relative roughness. Okay, we know Reynolds number, right? So he determined the relation between epsilon over D, Reynolds number, and the friction factor, and he come up with this correlation that we are kind of presenting it here. The only problem for this equation that the F is in this side and also in this side, okay, which means that it is an implicit function of F, and the only way to solve this is by iterative methods. Okay, what is the most important thing about this equation is you can use it for a computer codes. So basically, like the computer will be able to handle something like this digitally, right? So you can find out the fraction factor from this equation by doing simple reiterative algorithm. But for other engineering, again, like it is other type of equation for that is explicit function of Reynolds number. You see here F here is only function of Reynolds number, and is giving you a range here. So if Reynolds number is above 3,000, less than 100,000, the value here is basically can be determined from this first side here, while the same equation here is almost the same as a Colebrook equation. Okay, we are not at the position to really discuss different kind of correlations, right? Just to give you an idea about like if I need to calculate the friction factor, the only thing that I need to determine is your roughness of the pipe, what is the pipe material, and then what is the Reynolds number, and then try to find out appropriate method of calculating this friction factor. Okay, I promise you in a few seconds here, you will see that this is becoming a very simple type of problem once we know exactly what parameter we need to get in these pipe flow problems. This is just to give you an idea about the difference between laminar and turbulent flow. The laminar case is a velocity profile we call it a parabolic profile. Okay, while for turbulent flow is almost like a flat profile. Okay, turbulent flow is more mixing, which means that you are expecting the velocity to be a little bit varied by small little percentage from the maximum maximum velocity. While, you know, for laminar flow, the velocity at any point is a big difference between the maximum value and the velocity at any point, which means that laminar flow and turbulent flow will have a different, characteristic, which is in this case, we have to find out the friction factor for the laminar case versus the turbulent case. Laminar case is straightforward, okay? So F for laminar case is 64 over Reynolds number. RE or RN, both are, you know, referring to Reynolds number, okay? While, you know, for turbulent flow, F here is, we have to determine what is this F here, either from Colebrook equation or from, other methods, okay? Roughness, we are very exaggerating here in this figure here. So we are showing the pipe as if it's like you can see with a micrometer the variation in the, in the pipe surface. So the relative roughness is basically the, basically if you go and measure, the variation of the piping thickness here, you can see, this variation as considered to be what we call the roughness. And the roughness here is measured in the same lengths or the units of the diameter. So the absolute roughness is epsilon, okay? The relative roughness is epsilon over d. So how much is like, those kind of, protrusions or like, the non-smooth surface of the pipe versus the diameter of the pipe. So we call this is our relative roughness, okay? For different material, you will see, the roughness here given in millimeter or in feet, depending on the units that you are talking about. The uncertainty of the roughness here, because there are some variation in this roughness based on the value that you are measuring. But basically, this table here is presenting you as the most common material that we use. Let's say, for example, sheet metal versus stainless steel, riveted pipe, rusted pipe, like, iron, cast iron pipe, right, galvanized pipe. You will see the roughness is different as you, not only the material, but also the way that this material is manufactured. So did we like, did we create these piping by extrusion or by casting, right? So you will see that the roughness is different because of the machining process that is used to manufacture those pipes. Okay, even for glass here, you will still see, we call it the smooth surface here, but even there are some other table actually giving you this glass, but it's going to be very, very small value. Okay, glass can be considered as a smooth, but again, the roughness here is not zero. It's like we just call it smooth here because I'm gonna in a few seconds here I will tell you why we refer the smooth as glass here, and we're gonna use it for different kind of charts here. Okay, concrete, rubber, woods, all this material roughness is given in these tables. Now, as a practical, from a practical perspective for engineer or like even technicians working around facility that they want to calculate like, the friction losses or the friction factor, instead of like using a computer code to, use this Colebrook equation, we use what we call it a Moody chart, okay? So this Moody chart here is a graphical representation of the Colebrook equation, okay? The guy like, developed all these experiments, he plots the relation between all these, parameters. So we know that friction factor is a function of Reynolds number and epsilon over d, right? So that's why you will see here, you can see that this is your Reynolds number, this is your friction factor, right? And this is what we call it the epsilon over d, okay? So every line, so this line here representing epsilon over d of 0.004, and this line is not a straight line, it's straight line very far in the in the very high Reynolds number, but it goes like this, and it's kind of tilting like this, and this is all experimental data. Okay, so this line here is the line representing constant epsilon over d. Okay, and on the x-axis this is a logarithmic scale of Reynolds number. So you will see the Reynolds number here is 10,000, or, you know, sorry, here is 10,000. So this is 10 to the power 4, right? So as you go in this direction, the number is increasing. For example, here, this will be like 100,000, and this is like, you know, 1,000,000 and so on, right? So you just go and look at this. 2,000 is here, right? You see here, this is 1,000, this is 2,000, and you'll see below 2,000, there is no, like, it's only one line here, okay? Relating Reynolds number and the fraction factor. You remember, F for Reynolds number is 64 over Reynolds, right? Which means that it's not function of epsilon over d, and that's why the line here is representing, you know, this constant slope line between Reynolds number and the fraction factor. Okay, so what you need to do in order to determine this fraction factor from this chart is find out your Reynolds number. So let's say, for example, if it's like, you know, 10 to the power, like 100,000 here. So you can go in this line. If this is your epsilon over d is 1,004, these are the point where you want to get, and then you can go inside this and find out your, the fraction factor value. Okay, so the Moody chart considered to be a very simple graphical representation of the relations that we were talking about, the Colebrook equations and other equations. Okay, so now just to conclude what we what we talk about here, the fraction factor is an important characteristic or important parameter in order to calculate the losses between 2 points in a straight pipe. Okay, so if you have a straight pipe, you have a fraction losses. These fraction losses is a function of the fraction factor. This fraction factor for laminar case is very simple, 64 over Reynolds number. For turbulent case, you have to find it from the Moody chart. That's it. Okay. Let's look at this problem and just try to see, like, you know, what we have for this. So we have an oil with density of 900 kilogram per meter cube. The kinematic viscosity is 0.0001 meters squared per second. The flow rate is given as 0.2 meter cube per second through a 500 meter of 200 millimeter diameter cast iron pipe. So I have a pipe, straight pipe. Okay, the length of this pipe is 500. The diameter is 200 millimeters. Okay, the flow rate is 0.2 meter cube per second. The viscosity is given for this fluid, and the density also given for this fluid. What he is asking you to determine the head losses. Okay, and the head losses here is because the Bernoulli equation is presenting the, you know, every term in terms of head. So the pressure head, the velocity head, the kinetic head, right? That's why the loss is going to be a loss head, right? So what will be the losses in this case? If it is a straight pipe, that means we have only friction, right? So, and then he's asking what will be the pressure drop if the pipe slopes down 10 degrees in the flow direction. Okay, so it's basically like this. This is 10 degrees, this is 0.1, this is 0.2. I need to find out losses between 1 and 2. Okay, what will be the losses between 1 and 2? If I put Bernoulli equation between 1 and 2, okay, I can find out the pressure B1 and B2 in the second. Okay, so B1 over gamma plus Z1 plus V1 square over 2G equal B2 over gamma plus Z2 plus V2 square over 2G plus H losses between 1 and 2. Okay. Do you agree with me that V1 and V2 are the same? Yeah. So this V, so I don't want to call it 0. These two terms are cancel each other, and this loss in the between 1 and 2 is only H loss fraction, right? So I just call it H loss fraction. Okay. So it looks like I need to determine this H loss fraction, so I can go back here and find out the pressure difference here. Okay. How can we determine, this H loss fraction? Okay. So now, what would be the process here? I know that H loss fraction is F L over D V square over 2G, right? So it looks like I need to find out F. And in order to find F, I need to find out what? Yes, first line, excellent, right? So we need to find that either turbulent or laminar, right? So we need to find out whether the flow is laminar or turbulent, right? So in this case, the first thing that we have to do is like find out the velocity. The velocity here is Q over the area, right? The velocity here is 0.2, right? And the area here is 1 pi over 4. The diameter here, is it the diameter? 200 millimeters. Yeah, diameter. So it's pi over 4. The diameter here is 0.2 square, right? So if I need to find out this value here, it is basically 6.4 meter per second. So this is basically the velocity, okay? To find out Reynolds number, because I need to find out if this is laminar or turbulent, it's V d over nu. So this is a nu, which is a kinematic viscosity. Remember here that the viscosity that is given in this problem is a kinematic viscosity. It's not a dynamic viscosity, right? V here is 6.4 times the diameter here is 0.2 meter, and the viscosity here is 1.0001. Right, real number here is 128000. Okay, what does that mean? Turbulent flow, right? Because this is greater than 2300, right? So this is a turbulent flow. And for the turbulent flow, in order to find out the friction factor, we need to find also the relative roughness, right? So if you remember, so epsilon over D is now the diameter is 200 millimeter, and epsilon, I need to find epsilon here. So if you go, this is a cast iron pipe, is it? Okay, so the cast iron here in this table, this is a cast iron, and in millimeter, it's 0.26. So epsilon is 0.26 millimeter. Remember, many mistakes is like, when people are using the table, finding out the epsilon, for example, very simple, right? Make sure that you are using in this unit here and unit here the same, right? So if this is 0.26 millimeter, the diameter also has to be in millimeter, which is 200 given in this problem. So epsilon over D here is 0.0013. Okay, so it looks like I have epsilon over D. I have Reynolds number here. So this is Reynolds number, right? So basically, I just need to go to the Moody chart to find out, basically, find out F. Okay, so let's use this. I suggest that you see here 2, 4, 5. So you can just convert this into, okay, 1.28 10 to the power 5, right? So, okay, so you just count how many and just leave 1 here. So it's 1.28 10 to the power 5, okay? if I look at this, this is what? This is 10 to the power 5. This is the 10 to the power 5. This is 2 times 10 to the power 5. So what we have here, we have 1.28. So it's about 1.3 10 to the power 5, right? So we can say, for example, in this case, so this is 1.5, right? So it's something like here, right? So I can just say, and it's going to be approximation, of course, right? So you're going to be around the same kind of value, right? It doesn't have to be perfect. Right? I'm using an order here, right? Okay. And then what we have for the relative roughness is 0.0013. Okay, if you look at this, 0.001, right? If you look at this, 0.001, this is 0.002, okay? So which means that this middle point here is 0.0015, all right? Which means that something smaller than these values, right? So approximately like this. So we can just say, we just go between the line, between this line here and this line here. So try to draw a line in between. Okay. So it looks like this is a point, right? I'm just exaggerating with a circle here, but this is a point where you want to have your, from the table, what table? This epsilon already? It is cast iron. This is iron. This is cast iron, right? So it's basically the roughness is this, right? Okay. Okay. So basically I have this point here, so I can just go and okay, so basically I can get this point here. Okay. So if this is 0.2, so this is 0.3, 0.4, this is 0.5, right? 0.1, 2, 3, 4. So it's less than 0.4 to 0.24 and more than 0.023. So it's basically like, you know, I don't want to, like, you know, say any number in between. I can just take the middle, right? So I can say this is 0.20025. 2, 3. Yeah, all the line of relative roughness are curved. Yes. So that's why when you plot the line, why did you curve your, okay, so all the line is curved, and again, like, you know, the idea for you guys here, because this is not a digital computer, right? So it's kind of a graphical representation. So you will get a number that is close enough to the value for the roughness, right? You are not going to get something here or something here, right? So you're getting something very close here, right? So I can actually just share with you the values that we are getting here, and you know, I think I get it from the software I have for the fraction factors, because all this is kind of in the computer as Colebrook equations, right? But you know, there is going to be some tolerance, right? So if you get it 0.00, I think it's, is it? So 0.0235, for example. Sorry. So F here is, oops, sorry, what is yeah, 0.0235, something like that. Okay. So we're not expecting you to be that, close, but it's 0.02, right? So it's not like 0.01. It's not like 0.03. It's within the range of 0.02 something, right? Okay. So once I found this F, I can just say our H losses here. Okay. H losses is F L over D V square over 2G. So now I can just put this number here, 0.00, sorry, 0.0235 times L, which is it 100 meter, I guess? Oh, it's 500 meter. So it's 500 divided by the diameter. Remember, this is units here in meters, so you have to convert the diameter in meters. So it's 0.2. Velocity is 6.4 squared divided by 2 times 2, 9.81. The gravitational acceleration. So I can calculate H losses. And H losses here, this is your friction losses, because once you have a straight pipe, you have no other type of losses. Is only because of the friction between the fluid itself and the fluid and the wall. And all this is considered in this equation. So H loss fraction here is about 1.7 meter. Why meter? Because this is head, right? So the the unit at the end will be in the terms of meter. Now into equation 1. Where is equation 1? This is the equation that we put, the Bernoulli equation, if you remember, the pressure variation, Z, and the losses, right? So now when we have 10 degree inclination, so this is Z1, and it is inclined in the direction of the flow. So Z1 is here, Z2, let's say it is a reference point. So what is this value here? What is the difference between Z1 and Z2? Exactly, right? So it is 500, sine 10 degree, right? And Z1 is greater than Z2, right? So yeah, I agree with you about the minus here, because Z2 minus Z1 will be minus, right? So so in this case, Z1 minus Z2 equal to L sine theta, which is 500 sine 10 degree. Okay. Now if I take this equation now, so B1 over gamma minus B2 over gamma is going to be equal to Z2 minus Z1 plus H loss fraction, right? So this term here is minus 500 sine 10 degree plus 117, right? This will give you the value of the pressure divided by gamma. So this B1 minus B2. Gamma is specific gravity, right? So which is basically rho G, right? Because gamma is rho G. And rho is given in the problem, right? So you can say, for example, here, delta B, which is your B1, B2 is equal rho G times minus 500 sine 10 degree plus 117. Rho here is, I believe it was 900. Oops. 900, yes. This is a 900, G here 9.81. So delta B calculated is about 265,000 Pascal, okay, or 265 kilopascal. Pascal here because all the unit is in the SI unit, basic units. So now you divide by 1,000, you can convert it to kilopascal, right? Everything is clear here. Any questions? Yeah, 500 sine 10 or sine 10 times 500. Okay, yeah, I don't know what's the difference. Yeah, any questions on this? Guys, any questions? Why you are silent? Is it hard? Did I lose you? Anybody here? Oh, no questions. Okay. But do you have any? Okay, so everything is clear, kind of like, so it's a very straight kind of, systematic way of getting the H loss fraction losses, right? So you have the, the equation, we call it the Darcy-Weisbach equation, or this is the H loss fraction as a function of the fraction factor. The fraction factor is always will be the case where you try to determine these fraction losses, right? And if it's a laminar flow, it's a very straightforward. But if it's a turbulent flow, we're going to find out it using Moody charts, right? I'm not expecting you to, use a lot of correlations, at this time. But just to give you an idea, there's a lots of softwares available for calculating the fraction losses in fluid flow by providing those numbers, because at the end, it is a matter of computer algorithms kind of, calculating from this equation or reiterating until you find this value. Okay, I'm not gonna continue for the next part of this topic, but just an introduction to the next lecture. Not all the time the problem is simple like that. Okay, in real life, you are designing a pipe. Okay, so if you are designing, that means you are looking for the diameter, right? And if you are looking for the diameter, now you don't know what is the velocity in the pipe because you don't know the area of the pipe. If you don't know the velocity, that means you don't know the Reynolds number. So you don't know Reynolds number, you cannot find out the friction factor. But now we need to find out the friction factor to find out the H losses, to find out the flow rates. So you see here, so a design problem will be a reiterative problem. So if you're trying to look for, if you have a pipe that is, already have the flow rate and everything, you just need to find out the pressure drop, that's fine. This is what we did in this problem. But if you have a design problem, finding the flow rates or finding the diameter of the pipe, it is becoming a design problem. And now we have to do some, reiteration, have to assume one thing and then calculate it and see if this assumption is correct or not. Okay, so this is what we're going to do for next lecture. Okay, guys. Bernoulli equation in every unit in the Bernoulli equation in not in meter, in the unit of length, because we can use a different system, British system, for example, feeders and stuff like that. But it is, yes, it is unit of the length. In this case, in the SI unit, it is in meter. And just go back to the lecture that we talk about, representation of the Bernoulli equation in this format, because we introduced something called hydraulic energy line and hydraulic gradient line. And the importance of getting the Bernoulli equation in this term, it can be nicely representing all the part of the energy or all the terms of energy in terms of head, right? That's why the fraction losses here becoming also a fraction loss, a head fraction losses, right? The losses here in terms of head as well. Okay. Any questions? Okay, I'm gonna stop sharing my screen here and stop the recording. If people are interested to ask questions, no problem. We'll be able to solve problem set 6. Yes. Yeah, no problem, guys. I think next week will be next week will be this the flow and piping problem. And then we're going to continue also in our lecture talking about, like, you know, the solution of other problems. We're going to solve a few more problems to get more familiar with of these topics. Okay, guys, you take care. Stop recording.